So before that, let's just quickly look at what we did in lecture number 23. So 23 was about Bell's inequality. Bell's inequality was an inequality proved mathematically by Bell, in which basically he constructs a correlation and then proves the limit that correlation can reach within quantum mechanics as well as within the hidden variable theory. And that's how the proof goes, that the Bell constructs a situation where we have a source of two photons. It could be quantum mechanical source, or it could be hidden variable source, in which the two photons are from two independent sources. These photons are then detected, and one detects A and B, these two variables for those photons, which are the two dichotomic variables. That means they can take values plus minus 1 each. Before A is measured, there is a polarizer right for the first photon, polarizer for the second photon, and then depending on the value of this polarizer, the orientation of the polarizer, then one looks at what is the value of A and B, which can again just be plus minus 1. So for such a situation, one constructs this correlation function, which is A theta 1, B theta 2, ensemble averaged over many measurements. So within the hidden variable model, this correlation can be written as A theta 1 lambda, B theta 2 lambda times rho lambda d lambda, where A theta 1 lambda is the outcome, that is outcome of A when polarizer is at theta 1, but this is decided by hidden variable or a set of hidden variables lambda. Again, the outcome at B when the polarizer is at theta 2 is decided by a set of hidden variables lambda. So we know nothing about these hidden variables as to how many of them are there, how do they actually affect A and B, but one thing we do know for sure, that the distribution of these hidden variables, they have to be normalized. And the other thing we know, that the measurement of the polarization, let's for example here, or of the variables A and B here, should not affect the measurement over there. So the strict non-locality is definitely assumed here, but we have these hidden variables in the theory which we know nothing about, except that these must be the distribution must be normalized. So within this hidden variable model, then Bell constructs a parameter called the Bell parameter, which is basically these similar type of correlation put together in this manner, where theta 1 prime, theta 2 prime are the four distinct values. And for the hidden variable theory, we have seen that this S has to be less than or equal to 2. That's called the Bell's inequality. Now for quantum theory, this correlation that we have constructed will have the simple form, that is, since this is a dichotomic variable, so A times B can only be plus 1 or minus 1. So it's the probability of getting, is the plus 1 times the probability of getting plus 1, and the minus 1 times the probability of getting minus 1. And this we have seen that this one is basically when this probability of getting 1 is when both the photons go through the polarizer, and one can also get a plus 1 when both the photons are going 90 degree to the polarizer. That means that they are going to the other port. And similarly for minus 1, and this probability is equal to the probability that the first photon is passing through the polarizer, other one is going at 90 degree, and vice versa. So we then saw that for this kind of correlation function, the Bell parameter can actually be less than or equal to 2 root 2. So this is of course greater than the 2, that is the limit for the hidden variable theories. And if an experiment shows that this value is greater than 2, then we call the Bell inequality has been violated. We also saw that if we choose these values theta 1, theta 2, theta 1 prime, theta 2 prime to be this particular set, then the Bell parameter can actually be 2 root 2. This is just one such set. There can be infinite number of such set of theta values for which S is 2 root 2, but there is this set for which S is equal to 2 root 2. And then if we can experimentally show, then that's the experimental violation of Bell inequality. So from Einstein's arguments and from Bell inequality, we understand that entanglement means simultaneous correlation in two conjugate variables, and the inseparability of the two particle state into individual particle states. Again, these two are not two independent conditions, but they are pretty much interdependent. So we have seen that three kinds of entanglement. These are for the continuous variable, that is entanglement in position momentum, entanglement in time energy, entanglement in angle and OM, and then we can also have polarization entanglement. Again, we have the simultaneous correlation in two conjugate bases, and also that the wave function, two particle wave function is inseparable. So this is coming out from the Einstein-Podolsky and Rosen argument that this conditional uncertainty can be less than h bar by 2. And so there can be two generic ways for verifying entanglement, and one of them is through the EPR correlation measurement. When we say EPR correlation measurement, we essentially mean the measurement of the correlation of this form. That means the conditional Heisenberg uncertainty correlation measurement. The other one is the demonstration of Bell's inequality violation, which is what we did in the last lecture. Now this EPR correlation is suitable for verifying entanglement in the continuous variable system, because for continuous variable system we can construct this conditional Heisenberg uncertainty. So for position, momentum, time, energy, angle and OM, EPR correlation measurement or the conditional Heisenberg uncertainty measurement is quite suitable for verifying entanglement. That means if we do the experiment and if we do find that the delta x conditional delta p condition is less than h bar by 2, then we can say that yes, the two particle state, it does have entanglement in position and time. Similarly, if we do an experiment and find that the delta t conditional times delta e conditional is less than h bar by 2, then we can say it's entangled in time and energy. Now this demonstration of Bell inequality violation, this is suitable for verifying entanglement in finite dimensional system. Either it could be 2 qubit state or 2 qubit state, where d can be anything other than 2. So for finite dimensional state, Bell inequality is another alternative for verifying entanglement, because for finite dimensional we cannot have this uncertainty of relation, but Bell inequality will then help us verify entanglement there. So again, let me just point out that verifying entanglement is not the same as quantifying entanglement. In verifying entanglement, one only proves that yes, the entanglement is there in a certain degree of freedom. But how much entanglement is there, that we do not get through either EPR correlation measurement or through Bell inequality violation measurement. Of course, there is if this conditional uncertainty value is much smaller than h bar by 2, there is a sense that there's probably more entanglement there. Again, or in the Bell inequality violation, if s value is much larger than 2, then there is also a sense in which we can say there is more entanglement when there is a larger violation. But this is only in a qualitative sense, but these are not a quantitative value for saying how much entanglement is there. That's a very separate discussion, and we'll have a separate lecture for going through how entanglement is actually quantified. So today we are just going to do entanglement verification. Okay, so there have been several pioneering experiments actually to show entanglement, and here first I will list out the experiments that have been done to verify entanglement in the continuous variable system. So we'll start with position momentum entanglement. So we have seen the wave function that Einstein, Podolsky and Rosen construct in this paper, but this was the wave function that we got when we derived the two particle wave function coming out of parametric down conversion, and we again see that this is a state entangled in position and momentum. So of course this state is written only in the momentum basis, but we can also have a position representation for this, but this is a state entangled in position and momentum. Now using such a state produced by parametric down conversion in 2004, there was this experiment that actually reported the EPR correlation measurements, that means the conditional Heisenberg uncertainty measurement that was less than h bar by 2. So in this experiment we have a laser and this BBO crystal, so it produces parametric down conversion. The laser is blue and the entangled photons are red. So first they are separated, the blue goes this way using a prism and then red goes this way. So signal photon goes in this direction, idler photon goes in this direction. So this is a type 2 down conversion, collinear type 2 down conversion. So here we separated the pump from the signal idler. Now signal idler, since they have two different polarization, so signal, if this is horizontally polarized and this is a polarizing beam splitter, so signal if it is horizontally polarized, if it goes this way, and idler that would then be vertically polarized, it then goes this way. So signal goes this way, idler goes this way, and then we look at the correlation of these photons in the position and momentum basis. Now the EPR correlation measurements we want to do right after the crystal. That means the photon that just come out, what exactly is the position correlation and momentum correlation of those photons, and then based on that we'll then look at the conditional Heisenberg uncertainty. But of course one cannot put the detector right in front of the crystal. So the way it is done is that one images this plane of the crystal at this double slit at the slit plane. So that's the imaging distance, and that's the object distance, and that's the imaging distance, and here we have a lens. So using this lens, the output face of the crystal is imaged onto this slit plane. Similarly, this output face is imaged onto this slit plane right over here in the idler arm as well. So once these are imaged, this is like imaging this crystal right over here as well as over here. And now we can do the position correlation measurement. For that, one puts a slit over here and fixes it. That is, so now if we detect anything here, that would be detecting a photon with this particular position. And with this being fixed, then one puts a slit in the other arm and then slides this slits across the beam and sees what is the probability of coincidence. So here in this one we have fixed x1, and then we are putting this slit x2, and then it is going across like this, and that's the probability of coincidence. So this is the probability that having detected a photon at x1, this is the probability of detecting the photon at x2, where x2 is varying. And the width of this correlation, width of this coincidence detection will then be the uncertainty in the measurement of x2, that is of the second photon, position uncertainty of the second photon. So similarly, in this experiment itself, we can also measure the momentum correlation, and for the momentum correlation, again momentum correlation we want to measure it right at the face of output face of the crystal. So for momentum measurement, we go to the far field of this plane, and we know that the far field, we have seen this in Young's double slit experiment as well. We know that the far field is essentially the momentum distribution of whatever is the wave function here. So in this one, we looked at the position distribution of the wave function over here, and in this one we want to look at again the position momentum distribution of the wave function over here, which is by going to the far field. So once we are in the far field, here we basically have the momentum, the position distribution here is essentially the momentum distribution at this plane. So with this, again we put a slit, and now this time when we put a slit, this is like fixing the momentum value of this particle, and then we put another slit here and slide it across, and that is like for this given value of the momentum, what is the value of momentum, or what is the probability of getting a particular momentum over here. So again here we fix the momentum p1 here at some value, and for that fixed value then we slide this slit across. That means we are looking at different p2 value and looking at the coincidence. So this detection probability, or the width of this detection probability, essentially then gives us the uncertainty in the momentum measurement of the second particle. And so these are the experimentally reported values, and if we put them together, we find that this uncertainty product, that means the conditional uncertainty measurement of x, conditional uncertainty measurement of p, this is equal to 0.1 h bar, and this is of course less than h bar by 2. So this experiment then shows that yes, we have indeed seen the EPR correlation in position and momentum, and thus the photons produced by this BBO or this paramagnetic down conversion, these two photons are entangled in position and momentum degrees of freedom. So that's the confirmation. Again, how much entanglement, that we don't know, but it's just that they are indeed entangled in position and momentum. In most cases, again, either this is 1 1 or 2 2, they would pretty much be the same. That means the conditional uncertainty on the first particle or conditional uncertainty of the second particle, they would pretty much be the same, but they could in general be different as well. Okay, so this was the first experiment that was done in order to prove the entanglement in position momentum degrees of freedom. So this was in 2004. Then we look at time energy entanglement. So we have again seen that while deriving the two photon wave function in the temporal basis, we had derived this wave function, and this wave function is certainly entangled in time and energy because that's an inseparable wave function. So this indeed can be derived using the BBO crystalline through parametric down conversion. So then this was the experiment reported in 2018 using parametric down conversion. So that's a pretty complicated experiment. I won't go through every detail, but it's just that SPDC, it gives us signal photon, idler photon, and that's a detection mechanism for signal. So for idler, that's a detection mechanism for signal, and then we detect them in coincidence. This is a actual experimental setup. That's a laser. Then we have this is not the BBO, this is BIBO. That's another crystal used for producing entangled photons. So that's the BIBO crystal that gives us two entangled photons. One goes this way, the other one goes this way, and there is this entire detection setup for signal and the another detection system for idler, and then the two photons are detected in coincidence. But essentially what we are detecting here, just like position momentum in the other experiment, we are detecting that at a fixed value of the let's say idler frequency, what is the range of values over which signal can be detected, and that's the coincidence count as a function of omega s when omega I is fixed. It could be other way as well. Similarly, then we can do also an experiment where the arrival time of idler photon, once that is known, then for that a given arrival time of the idler photon, what is the time range over which the signal photon can arrive, and that is the probability for that. And when we multiply these two probability, that means the conditional arrival time, conditional uncertainty in the arrival time and the conditional uncertainty in the energy, this frequency, and then we just multiply that by h bar, that becomes the energy, and this is 0.29 h bar. Again, this is less than h bar by 2, so this proves the entanglement in time and energy. Again, doesn't quantify, but it does prove the entanglement in time and energy. There was another experiment. This is done as of 2020. I mean, we see position momentum was done in 2004, but time energy is now 2008 and 2020, because these experiments, time related experiments, are usually much more difficult than the position momentum type experiments. So in this experiment, again we have two entangled photons, but this time not through parametric down conversion, but through this four-way mixing process, in which we have these two pump photon, the WP, WC, and we get two entangled photons, that's called Stokes and anti-Stokes. So these are the two entangled photons emitted. Again, I will not go through the details of this experiment, but essentially one does a very similar measurement here, where the arrival time of one photon is known, and then we look at the uncertainty in the arrival time of the other photon. Again, knowing the frequency of one photon, we look at the distribution or the range of frequency over which the other photon can be found. So this way we find the uncertainty in time and uncertainty in frequency or energy, and when we put them together, in this experiment, the conditional uncertainty in arrival time and the conditional uncertainty in energy, this was 0.063 h bar. So this one was definitely much better than this one. Of course, both verify time energy entanglement, but here the results were much better, 0.063 h bar. So that was in time and energy. Similar experiments have been done in orbital angular momentum and angle basis. So we can have two particle state produced by parametric down conversion that are entangled in orbital angular momentum basis, and that this is usually the generic structure. So here we have a signal photon with orbital angular momentum LH bar and idler photon with orbital angular momentum minus LH bar, so that the sum is 0. But again, signal can have any L value or idler can have any L value, but whenever the signal is L, idler is minus L, LH bar or orbital angular momentum. Again, this is an inseparable wave function. So using such a wave function produced by parametric down conversion, this was the experiment done in 2010, in which EPR correlation in angle and OAM was demonstrated. So in this experiment, we have a laser. This is a BBO crystal. It produces two entangled photons. One goes this way, the other one goes this way, and we look at its orbital angular momentum correlation, and then then its angle correlation. So when we are looking at orbital angular momentum correlation, one puts a diffraction hologram through which one detects the, let's say, the signal photon at orbital angular momentum L equal to 0. Now this one is kept at L equal to 0, and then we change the orbital angular momentum of the idler photon, and then look at the range of L values at which idler has a probability of being detected. So here is the experimental result when signal is fixed at L equal to 0, and we change the orbital angular momentum value of the idler photon at which it is detected, then that's the probability we get. That means, of course, when signal is at L equal to 0, idler has all the probability of being detected at L equal to 0, but there is a tiny probability that it can also be detected at plus minus 1 and so on. So this was for the L. Similarly, we can do it for the angle. That means when the signal is fixed at some angle, and for this one we put this device where we have this narrow angular slit here as well as a narrow angular slit in order to define the angular position or angular location of the signal or idler photon. So this is when this signal photon has some fixed known angular position, and then we scan the idler angular position, and that's what we get. And again, correspondingly we can also get here the conditional uncertainty in angle times the conditional uncertainty in orbital angular momentum, and this turns out to be 0.15 h bar. Of course, this is less than h bar by 2, and then this does verify entanglement in orbital angular momentum and angle variables. This was the EPR correlation measurement in the 3 degrees of freedom, and although EPR had used the fact that this is a strange fact of quantum mechanics that one can have this kind of correlation, but now this strange fact itself is used for verifying entanglement. Okay, so now we'll go to the violation of Bell's inequality, which is actually used for entanglement verification in finite dimensional system, and then let's look at all the different experiments that have been done. So first, what Bell showed was the Bell inequality for the 2-dimensional system. So for 2-dimensional system, he basically shows that if this value s is less than or equal to 2 for hidden variables, and this has to be less than or equal to 2 root 2 for quantum correlation. So if s value is greater than 2, that means we can say that yes, entanglement is there. And the Bell's inequality can actually be applied when we have this 2-particle 2-dimensional systems, and these are also called 2-qubit system. And here we have this example we have in the polarization basis. In fact, these 2-qubit states are, I mean, this is just a slight digression here. This 2-qubit state is very important for quantum information or quantum computation systems and many protocols. So why we call it 2-qubit state? The bit is coming from the classical language, the classical unit of information, and when we say bit, B stands for this 2-dimensional thing, and here it is 0 and 1. That is a classical bit. In quantum, it becomes q bit, that means quantum bit, and quantum bit is also 2-dimensional, but here a quantum bit can mean 0 and 1 as well as alpha 0 plus beta 1, that means any superposition of 0 and 1. So again, in classical, when we say a bit, we mean 0 or 1, 0 and 1, these are the 2 states one can have. But in quantum, when we say a bit, when we say a qubit, we mean 0 or 1 or any superposition of these 0 or 1, that means a 2-dimensional state space. When we say 2 qubit, we mean that we have 2 different particles. Q of course is for quantum, bit is for 2-dimensional. When we say 2q dit, again 2 is for 2 particle, q is quantum, and d means a d-dimensional system. So this Bell inequality that we have studied, that is for the 2-particle 2-dimensional system. Of course, entangled 2-qubit states, these are basic ingredients for many quantum information and quantum computation protocols. And the original Bell inequality that was done, that was meant actually for 2-dimensional degrees of freedom, that is polarization. But we'll also see that the Bell inequality, the 2-dimensional version of Bell inequality, can also be used, and the entangled q bit state can also be generated using continuous variable systems. But we can also have Bell inequality for entangled 2-particle d-dimensional system, because one can in general have entangled 2 qubit states. And there was a Bell inequality that was derived for d-dimensional system, and this was in 2002. So Bell's was in 1964. That was for 2-dimensional system, 2-particle, but the 2-particle d-dimensional system, this was done in 2002. Okay, so now let's look at the different violations of Bell inequalities that have been reported, and also how a continuous variable system can be used in order to make 2-qubit states. So first, polarization. This we have seen that in this was the very first experiment that shows the violation of Bell inequality, and hence can prove that yes, quantum mechanics is indeed correct and there cannot be an alternative to quantum mechanics. So here we have the quantum state, the 2-qubit state in the polarization basis, and this is HV plus VH. And there was this experiment that was done in 1995. This showed a much better violation of Bell inequality, and using the photons produced by parametric down conversion. This was in atomic cascade, and this was in parametric down conversion. So here we have a type 2 polarization entangled photon. It's coming from the BBO crystal, and it's a type 2, that means signal photon that is horizontally polarized, idler photon that is vertically polarized. And the phase matching, the way it works is if you detect a signal here, the idler is detected at this point. That means just a diametrically opposite point. So of course, if you detect a signal here, the idler is over there. But at this point, the overlap point, one can have either a signal which is horizontal, or one can have idler from this circle which is again vertical. So if you detect a photon, it could be either horizontal or vertical. But if it is horizontal, that means it is coming from the signal circle, and hence at this point we will detect a vertical that is coming from the idler, and again vice versa. So that's the state that such a phase matching system will actually produce. With such a phase matching, then this experiment actually verified that if you look at coincidence, we get this kind of dependence that shows the cosine squared theta 1 minus theta 2 type dependence that we have seen for quantum correlation. And in this case, the Bell parameter was measured to be 2.55 in the polarization basis. Again, this is less than 2 root 2, that is 2.82, and thus it demonstrates the violation of Bell inequality. There was this experiment done in 1999, and this was with HH plus VV type state, again a 2-qubit state. This was produced using 2 type 1 parametric down conversion. So that's one type 1 parametric down conversion. This is another type 1 parametric down conversion, but this is rotated 90 degree with respect to each other. So that's why the cone from the first one is both signal is horizontal, idler is horizontal, and for the second one, the signal is vertical, idler is vertical. And if you put them together, the state that we get is HH plus VV, because these two are essentially coherently superposed because they are being produced by the same laser that is polarized at 45 degree. So in this setup, when we do the experiment, we see a very similar cosine squared theta 1 minus theta 2 type dependence. And in this experiment, the Bell parameter that was measured was 2.70. So this is of course much better than the value obtained here, and so this shows a much better violation of Bell inequality. So this was in the polarization degree of freedom. So of course, polarization is a 2-dimensional system. So, and Bell inequality was meant for a 2-dimensional system, and these are the 2-qubit states that can actually be generated in the polarization basis or polarization degree of freedom. But we can also use the continuous variable system in order to make a 2-qubit state, and thus also do the Bell violation there. So 2-qubit state in the momentum basis, the first experiment was in 1990, and in this experiment we have seen earlier as well. This was 2 different directions was chosen such that the state that is coming out of down conversion is effectively of this form. That means when the signal is has a direction q1, idler is q2, and when the signal is q2, idler is q1. And for this experiment, the Bell parameter was measured, and it was found to be 2.21, again less than 2 root 2. So this shows a violation of Bell inequality, and this shows that this is how we can make a 2-qubit state in the momentum basis. Similarly, we can have 2-qubit state in the position basis. This was an experiment done in 2007. In this, again a BBO down conversion, and we are putting a double slit here and double slit over there. And the double slit again makes a 2-dimensional basis. Again, position is a continuous basis, but a double slit is just constraining the photons of the field to come out either from this or from that, and that's how it's making a 2-dimensional subspace. So in this case, the kind of 2-qubit state we can make is of this form. We can also have the violation of Bell inequality and 2-qubit state generation in the time energy basis. Again, I will not go through the details of this. This was an experiment done in 2002, and one can show using this setup that one can indeed make a state in the one can make a 2-qubit state in the time in the time energy basis, and any Bell inequality violation done with this kind of state verifies time energy entanglement. One can also have 2-qubit state in the frequency basis. Again, a complicated experiment, but the whole point is that yes, one can indeed have a 2-qubit state using just the frequency, and if one does a Bell inequality violation here, that verifies time energy entanglement. Finally, we can have a 2-qubit state generation in the angle and orbital angular momentum basis. So and here one can, instead of putting that double slit, we can put double angular slit, and thus define the bit or the qubit space. And finally, we have this 2-qubit state in the orbital angular momentum basis. Very similar experiment that was done for the verification of for the measurement of EPR correlation. Here also we have this signal photon, idler photon, and then we one basically post selects the field here such that the field that is effectively coming out is of this form. That means whenever signal is L1, idler is L2, signal is L2, idler is L1. Or when talking about orbital angular momentum, this is orbital angular momentum indices. When talking about orbital angular momentum, this is L1 h bar, L2 h bar, and whenever signal is L2 h bar, idler is L1 h bar. So for such a 2-qubit state, there was this Bell inequality experiment done in 2009, and the value of this parameter was found to be 2.69. So then this shows that yes, the Bell inequality has indeed been violated, and this experiment proves the existence of angular position orbital angular momentum entanglement, and that this is a valid way of producing a 2-qubit state. Okay, so far we have done different methods and experiments that have been carried out in order to demonstrate entanglement, and also to kind of show the different ways in which 2-qubit states, which are pretty necessary for quantum information and quantum communication protocols, how they can actually be produced. So we will stop here, and in the next lecture we will look at entanglement quantification. Today was just entanglement verification. So next lecture we will look at entanglement quantification. That means what are the different ways in which entanglement can be quantified, and also in fact entanglement can't be quantified for all kinds of states. So we'll look at only those states for which entanglement can actually be quantified. So for today's lecture we'll stop here. Thank you.